Thank you everybody for being here, and thank you for being here for my talk about plate tectonics on Earth and alien planets. I'd like to acknowledge some people who've been on the way very helpful in the last few years, from Doris Breuer, Adrian Nordic, Sarah Seager, and Lena Nowak. And I'm gonna right now jump into the subject as time is short. The major motivation, what we're actually trying to do is to in some way connect plate tectonics again to some more basic and simple thermodynamic principles, just to get a deeper understanding of what's really thermodynamically initiating or maintaining plate tectonics. And the major thing we try to do in this first order is to also understand how planet conditions throughout time impact the initiation and the maintenance of plate tectonics. And the first aspect is a kind of a more quality-related aspect, where we try to understand are, let's say, radiogenic heat sources increases, or surface water, or maybe iron to magnesium ratio, planet mass, heat, core size, whatever that characterizes a planet. How do they impact plate tectonics? Are they suppressing it, or are they supporting it? But moreover, what we try to do, and what the major goal was, is to develop a metric specifically for 1D models, because when we investigate this whole realm, we unfortunately have to rely on 1D models because we can't do it effectively with 2D and 3D because there's too many parameters. So what we really want to study is develop a metric to say, how does a change in a property impact plate tectonics? And I'm trying to illustrate it over here. Let's imagine we have normally rock, and we change rock in a planet with gummy bears. I do really find it very illustrative to understand that. And then we look in time, like 13 billion years here, how does this change help to drive plate tectonics or not? And we managed to plot it somehow, in a scale, log scale, and we see that in the first 5-6 billion years it's helpful, and then it starts to not be helpful. And so what we want to do as well is that's going to help us to understand and give a number to, like, if we do another change, example, we change the surface temperature, increase it, how does this relate to a change in composition, and especially try to understand whether there's a time impact. So, because mostly this is just a quality thing, understanding how does it work, but this is specifically telling us when in time did it work in what way, and how do they relate to each other, which ones are more important. Because we know that plate tectonics is a complex feature where many things matter, but we want to put them in relation to each other, knowing which one is more important when. And the reason why we focus actually on combining 1D and 2D and 3D models, because 2D and 3D models help us very much to understand what's really going on and to be more close to the real nature that's happening out there. But the 1D models are simply neat because we're trying to simulate a realm that is too large for 2D and 3D models to handle. Now, right into the models, I'm going to be very quick about that. We are usually having an approach where we combine 2D models, 2D spherical and interior evolution models, and we also combine them with 1D thermoevolution and plate tectonics models. And the 2D models are mostly used to gauge our 1D models to understand what we're doing is also right. And in the 1D models, we then allow planetary structures to vary. We look at planets with no cores, planets with Earth-like cores, planets with much larger cores, can change the planet mass, composition, surface temperature, and then we simulate something like 500,000 of planets during 13 billion years, which we believe now is approximately the age of the universe. It's actually 13.5, but 13 is just a really nice number. And so we simulate in those planets and the thermoevolution of those planets and plate tectonics on those planets with 2D models and for specific cases, and 1D models for many other cases, and try to understand what's happening and how different properties then and conditions impact plate tectonics. Now, one important thing, or two important things, are those little brackets over here. The problem with 1D models is, and I'm going to talk about it later on, is that I believe we relied too much in the last few decades on just trusting our little parameters that we put in there, and we raised doubt that maybe we have to change those. So that's why we allow a large uncertainty in our scalings for heat flow, flow velocities, and flow geometry with Rayleigh number. And specifically, which you're going to see later why that matters, we look at two different stress scales. We look at shear stresses and normal stresses that are interacting with the lithosphere. And we allow this big uncertainty just because we want to understand a bit deeper what is really driving plate tectonics, and understand as well, when we do our models, what do we really figure out? Right now in this talk, I'm going to focus mostly on the 1D results because they really help to illustrate things very well, but they're all in agreement with our 2D results. Well, for the 1D model, I got to just quickly explain what we will look at when we talk about plate tectonics. And we'll look at a few criteria, which I call kind of like metrics, plate tectonics metrics. And the first one is just the typical focus on failure. And so what we do over here is we're looking at just at the driving stress that is causing failure in relation to a yielding stress of the thermal and elastic lithosphere. And what we then look at is, we say we change a property. As example here, as I said, we change from rock to gummy bears in composition. This can also be a surface temperature increase or, or any other increase. And then we simply look, did this increase help to increase actually the driving for plate tectonics for failure or not? And we call this very interesting, the propensity of plate tectonics, because likelihood demands, unfortunately, a real probabilistic approach, which we don't have yet. And the important thing is, and that's what you see over here, the driving stress can be shear or normal, and we'll leave it open for the moment. Now, let's have a look at some results that we figure out here. And I'm trying just to give you a little insight into some of the catchy results, which you find out interesting, and which we are also putting in relation with our 2D models. So one first part is going back to thermodynamics and trying to understand from our evolution model, how does plate tectonics and the propensity of plate tectonics depend on interior heat? And the important thing is, as already mentioned, in the 1D model there are parameters for convective heat, for heat flow, for velocities, for geometry, and the stress type. Now, the important thing is, of course, we expect that the results depend strongly on it. However, they don't just depend strongly on those assumptions, they're enormously, in a complex way, sensitively depending on it. Because the whole thing is very nonlinear, and as expected, things will behave very nonlinearly. What we figure out is that if we look at this uncertainty space for the 1D models in parameters and stress type, we see that actually one parameter, which we call chi, because it's one of the Greek letters that's not been used yet that much, chi is a function of our parameters and the stress type. And the important thing is, we find that actually there's two thermodynamic, more or less, scenarios for parameters that are defined by being smaller than a critical value, which I'm going to explain in depth what it is, and such parameters that are larger than a critical value. We call the low ones chi-low systems and the other ones chi-high systems. Now, the important thing between those two different systems is, and we're going to see it later, that they actually determine how plate tectonics reacts to heat, the propensity of plate tectonics reacts to heat, and thus also later on how any condition on the planet or in the planet impacts plate tectonics. Now, what is this critical value, this chi critical value? This is more or less described in some examples over here. It's actually a parameter that describes the planet's properties. It depends very much on the rheology. I'm showing here this example how this parameter depends on the activation energy and it's a function as of the superadiabatic temperature contrast with the mantle. And as we can see over here example, by changing your activation energy, you have very different behaviors. Surface temperature is also impacting it, and many other properties. Now, the important thing to mention is that the chi value itself depends mostly on whether shear or normal stresses are being used. So if shear stresses are actually mostly driving plate tectonics, we see that actually for most parameters that we can use for thermoevolution models, the system is actually a chi-low system. So shear stresses and chi-low systems are very closely associated with each other. Normal stresses are mostly associated with chi-high. And the important why this is so interesting is because those two different domains define very distinct behaviors. As an example for the chi-low system, we see that no matter what kind of plans we model, if we increase the radiogenic heat content or the core heat content, plate tectonics becomes less likely, illustrated by negative values for the chi-low system, independent of time and planet structure and composition. The opposite is for chi-high. So the chi system, whether it's a chi-low or chi-high system, and that's also the type of stress that's driving plate tectonics, shear or normal, actually controls mostly how the propensity of plate tectonics reacts to heat. And the interesting thing is, we've been running now in the last 1 year some 2D studies, mostly looking at the stresses. Which kind of stresses are responsible, more shear or normal stresses, where they act, how they relate to initiation maintenance, and also to our evolution models. And so far, we have to say we don't know, we're not yet sure which one is actually the more realistic one. However, so far we see that chi low is actually most likely favored. So that means, in that case, if you would increase very much the radiogenic heat sources, you actually suppress plate tectonics. The important thing is, and I'm going to be a bit fast now because I see my time is running off, heat is, of course, something that can universally be transferred bijeectively to different changes in composition or structure. So by understanding how plate tectonics reacts to heat, we can understand how it directs to mass, to water, and any other things. And so I'm going to show you now how, for our chi low and chi high systems, what kind of findings we have. Example for planet mass. And this is a really interesting figure. So when we look at increasing the planet's mass, and that's been looked at in the last 7, 8 years very intensively, what we see, again, in the chi low and chi high system is that the propensities, and this is 0 here, this is 0 over here, depends very much on whether they're being chi low or chi high. Chi low system have rather propensities which are negative, chi high positive, which means simply for the chi low systems, which we think are more realistic ones, if you increase the planetary mass, actually plate tectonics becomes less likely. But the really interesting thing over here is, and there's a lot of color over here, just have a look first at the gray zone and at the red zone. The gray zones, we assume no conditions on the initial temperatures. We say we don't know how the planet is formed, if it was molten initially or very cool. And if we don't assume anything about initial temperatures, we see that it's not really clear, even for chi low and chi high. Sometimes increasing planet mass can be good for plate tectonics, sometimes bad. However, when we clearly specify and say, no, all planets actually start molten. They start molten and we start right below solidus. Then we have actually very clear information that for chi low, plate tectonics is less likely on more massive planets, and for chi high it's the opposite. And that's really interesting because it helps very much understanding why different groups concluded differently. No matter if they had 1D or 2D models, we can actually, what I'm not showing here, nicely track back and see which group was using what kind of conditions and how did they relate in a chi low space and how did it scale interior temperatures. And specifically telling us that initial conditions and the evolution matter very much. Now, another thing which is really interesting to see as well here, based on a model, we can also look at the initiation of plate tectonics and when it was most likely. And I will not go much in depth into this figure because I think I have 1 minute and 35 seconds, if that's right. The major point that comes out of here, independent of our models, you'll see that actually this is the propensity of plate tectonics. It always peaks in the first 500 million years. And interestingly, it peaks because it's actually controlled mostly by core cooling. So the core cooling initially is actually the major driver force that governs the plate tectonics propensity over here. And we're doing right now 2D models in progress to look how initially when we superheat the core as much as we can numerically, how it actually, if it helps very much more to initiate plate tectonics. Because that's what's being suggested actually here, a kind of hot plume origin for the initiation of plate tectonics. I'm going to just quickly skip this water cycle because that's actually just going to say what's coming out of that. The interesting part is when looking at water, how water impacts plate tectonics, we see that actually only surface water that can lead to vapor-saturated melting at subduction zone is actually helpful for driving plate tectonics. Otherwise, almost all the water effects we can include, whether rheology, melting, or thermal conductivity, are actually not really helpful because they reduce the convective stresses enormously. However, below subduction zones and vapor-saturated melting, where we really have oversaturated water, more or less supercritical water flowing up, that's the chance actually to get plate tectonics positively affecting by water. And the last thing, which I want to jump in here quickly in my last 10 seconds, is about surface temperature, which has been done also very much. And our perspective on this one is that, interestingly, again, it doesn't depend on the Carlow scenario, it's a robust conclusion. We see that actually for maintaining plate tectonics, so if you have already plate tectonics and keep on going, increasing surface temperatures are really not helpful because they're actually suppressing it, mostly because they're simply they heat up the upper mantle and they also lead to a contrast reduction in the upper mantle, which reduces the convective stresses very much. This is mostly in agreement with most people. Interestingly, for initiation, we found a weak effect, but an opposite effect. And this is to do that in our models, the communication between the surface, where the temperature change happens, and the interior is very weak when you have initiation, when you have water stagnant lit. And this decouples partially, only partially, thermally the interior from the surface, which leads to actually very thinning lithospheres, which help actually initiate plate tectonics. And that's really interesting because if you have very high surface temperatures, you can be in an unstable configuration where you easily initiate, but you can maintain. And I will right now jump to this part and come to this last slide, which we can leave as a conclusion as well. So the interesting thing which we see over here is we can develop a consistent framework, which is going back to the roots of understanding thermodynamic principles behind plate tectonics. We connect into 2D and 3D models to find a convergence between the good sides of both worlds. And the important thing which we see as well is that we cannot really trust that much the parameters normally used for 1D models. And we note and see that we actually really have to be much more careful when we do evolution models and use steady state 1D models for planetary evolution. And for 2D and 3D models, we also have to be careful, and specifically careful if we don't use realistic parameters. So those models that use realistic parameters are great because we're there. But the problem is, as we've seen, this chi-low, chi-high regime, so where you fall in, depends very much on this critical parameter. Now, this critical parameter, which separates these very distinct thermodynamic regimes, depends completely on composition and activation energy. Now, if we use unrealistic parameters, we can very easily fall in different regimes. And then we have to ask ourselves the question, what we're really modeling. And I leave you all there with the way forward for questions. Thank you. Thanks.